In order to estimate the solar insolation and the energy in kilowatt hour per meter square per day falling at a given locality on the Earth's surface, we need to understand the Earth-centric viewpoint and the parameters related to it. And therefore, I will briefly review the Earth-centric viewpoint and its related parameters before going into the maths for estimation of the solar insolation at a given place. Consider that an observer is well removed from both the Earth and the Sun. He will see that the Earth revolves around the Sun in an elliptical orbit, something like this, with the Sun positioned within the ellipse and the Earth goes around along this elliptical path. Let us position the Earth like this. This is the equator and this is the pole axis. Observe that the pole axis is tilted from the vertical by around 23.5 degrees. The Earth is spinning about its pole axis continuously as it is revolving around the Sun. The spinning effect is what is going to give the diurnal effects, the day and the night. Now let us say this position occurs on 21st March. I will talk about this later, but for now let us say at this position it is occurring every year on 21st March. Now the Earth is continuously spinning and moving along on this path, on this elliptical path, and let us say it comes to this position. And at this position I will mark it by again another picture of the Earth spinning with the same tilted axis, and this occurs on June 21st every year. Progressing further in time, the Earth takes this path and then reaches another important point here, and that occurs every year on September 21st. Of course, some literature says September 22nd or September 23rd, but for easy remembrance, I will keep it at September 21st. And then going further along, you will see that this is another important point, and I will mark that by another picture of the Earth, and this occurs every year on December 21st. March 21st and September 21st, these positions are called the equinoxes because the Sun is in the equatorial plane. It directly is in line with the equator. When I show you the Earth-centric viewpoint, you will see that the Sun aligns itself along the equatorial plane. And this line joining these two is called the equinox line. Now, this position is called the summer solstice. For the northern hemisphere, it is the longest day that will occur on June 21st. And you will see that the Sun aligns more towards the northern hemisphere, and the line passes through the 23.5 degree latitude, which is the Tropic of Cancer. And in the southern hemisphere, it is winter. Likewise, on this side, this is called the winter solstice, and this occurs on December 21st every year. And you see that the Sun aligns itself along this line where it touches the latitude Tropic of Capricorn, which is minus 23.5 degrees in the southern hemisphere. So it is summer for the southern hemisphere, and for the northern hemisphere it will be the winter. The line connecting the two solstice points, the summer solstice and the winter solstice, is called the solstice line. And the line connecting the two equinoxes is called the equinox line. I had mentioned that the extraterrestrial solar insolation is fairly constant. It varies between 1.33 to 1.41 kilowatt per meter square. So typically for these positions of the Earth points along the elliptic orbit, the following insolation values, data values are available. So at the winter solstice point, it is 1.41 kilowatt per meter square. And at the summer solstice point, it is 1.33 kilowatt per meter square. At the September equinox, it is 1.36 kilowatt per meter square, and at the March equinox, it is 1.38 kilowatt per meter square. Apparently, the shape of the elliptic orbit and the nearness of the Earth to the Sun would probably have brought about this small change in the value of the insolation. In this view, the observer is neither on Earth or the Sun, is away from both these planetary bodies. Let us move towards an Earth-centric viewpoint in order to get the insolation at a point on the surface of the Earth. We have the pole axis, the polar axis, tilted at 23.5 degrees from the vertical. So let us try to shift it and make the polar axis vertical. That would give you a better visualization for the Earth-centric viewpoint. So when we tilt the entire figure by 23.5 degrees, you see that the polar axis for the Earth appears vertical, and this will become the basis for the Earth-centric viewpoint. Now the Earth, a bit enlarged, is like this. You have the equatorial plane. This is the Tropic of Cancer and the Tropic of Capricorn. The Earth will rotate about its polar axis. Now observe this line, the line here going along and joining to the center of the Earth. So the line joining the center of the Earth to the center of the Sun. Now that is this line. And on 21st June, it appears to a person on the Earth, it appears the Sun is relatively in this position like this with respect to the Earth. Then if you go along and look at the winter solstice, you see that the Sun is aligned in the southern hemisphere. So it looks as though the Sun has moved down, and it is aligned in this fashion to the center of the Earth, and it is cutting the surface of the Earth at the Tropic of Capricorn at minus 23.5 degree latitude. And for both the equinoxes, the Sun aligns itself along the equatorial plane in this fashion. So for a person standing on the Earth, let us say a person standing here on the equator, it would appear as though the Sun is moving in this fashion annually. So June 21st, it would have reached the maximum point in the northern hemisphere, cutting the surface at 23.5 degrees north, which is the Tropic of Cancer, and then moving down, it reaches the September 21st equinox, which is aligned along the equatorial plane, and then as this continues, you will see that it reaches the December 21st winter solstice, which is aligned along this. It is summer for the southern hemisphere. And then as this continues to move up like that, you will see that this again starts to move up. The sun is ascending and reaches the March 21st equinox, and so on. The cycle repeats year after year. Now this is called the earth-centric view, and this is the view that we will be using for calculating the insolation at any given latitude on the earth's surface. One important angle that I want to introduce here is the angle between the equatorial plane and the line joining the center of the earth and the center of the sun. That is this angle. This angle is called declination, and it is denoted by the symbol delta. Remember this, the delta or the declination is the angle between the equatorial plane and the line joining the center of the earth and the center of the sun at any given time and day of the year. So the declination angle varies from plus 23.5 degrees to minus 23.5 degrees. Let us look at the model for the declination delta from the earth-centric viewpoint. So this is supposed to be the earth. This is the polar axis. It is rotating about the polar axis, and we saw that the movement of the sun over the year is in this fashion. The sun reaches a height where the line joining the center of the earth and the sun cuts the 23.5 degree latitude north, which is the Tropic of Cancer. And then as the sun swings to the winter solstice point, it intersects the latitude Tropic of Capricorn, which is 23.5 degrees south. And it is the equinoxes here during March 21st and September 21st. Now consider an arbitrary point here. The sun is on some day at this position. The line joining the sun and the earth is here indicated in red. This angle is called delta, which is the declination. So this is a variable, and as the sun is moving along in this arc, the value of the delta keeps changing. It reaches a max value here, which is 23.5 degrees, and the min value will be corresponding to this, and that will be declination value of minus 23.5 degree, because it is going in the clockwise direction from the equatorial plane. Now, how to go about obtaining a model for this variable delta? So if you look at the movement of the sun, so now take for example the equinox. Let us say March 21st. March 21st it starts here, then goes up, June 21st, then starts coming down, September 21st, then still going further down, December 21st, coming up again, March 21st. So this movement is one cycle. This has a resemblance to a sine wave. If you look at the delta function as a function of time over the year, as the function of the day number over the year from 1 to 365, it has a very close resemblance to the sine wave. So one very good model would be can be based on this sine function. Let us make some space. Let me push it up so that we have some space here. Let me push this up. Okay. Now delta can be written as 23.45 into sine 2 pi n minus 80 by 365 as shown here, where n is equal to 1 on January 1st, n is equal to 365 on December 31st. This is an empirical formula which seems to fit the delta with very close accuracy. You can get 0.1% accuracy with respect to actual values that you would find in ephemeris data or the almanacs. The delta declination is given in degrees. Observe that here 80 would represent, in terms of number of days starting from Jan 1st, 80th day would be 21st of March. So somewhere at the equinox. So when n is 80, sine 0, so you have delta 0, it's starting from here. As n is increasing, 81, 82, 83, so on, goes up here and then comes back and returns again back on March 21st to this point. So the sine wave is shifted in such way that at n is equal to 80, it is 0 starting at this point and also at the equinox, the September equinox.